So welcome back. So today is week 9. So last week we just finished the so last week we just finished the midterm test. So yeah, how is the midterm test? It's good. So anyway, I mean the final exam is going to be open book. So yeah, you have already passed the tough part. Okay, so from this week we are going to have one more lecture about GPS. So today we are going to talk about how to use the GPS data to estimate the velocity. Okay, calculate the velocity. So next week it's going to talking about the sensor fusion. So like how to integrate the information from two different sensor sources. For example, like GPS and together with odometers, like via odometers. Okay. So for example, using Kalman filtering and with maybe factor graph. So from week 12 and week 13, okay, we are going to have presentations. So as you can see from the blackboard, okay, I have upload the requirements for the presentation. So each student, okay, one student for one presentation. So for this year, because we only have 11 students, so 15 minutes for presentation and 5 minutes for QA. Okay, 15 minutes for presentation. So for example, for week 12, okay, we roughly have like 6 students to present. So each student will like roughly like 20 minutes, 15 minutes for present and 5 minutes for QA. So each of you need to prepare a slide. Okay, each of you need to prepare a slide so to present. And so this is, outline. For example, if you present a paper, so later I will mention the topics. So you need to increase the background. Background means we're going to talk about, for example, like the navigation technologies for Tesla or navigation technologies for Google's auto-driving cars. So for example, we can talking about the drones. It's also okay. So the motivation means, for example, you look into a paper and present the content from a paper. So why this paper is important? And also the methodology means like maybe there are some equations, some algorithms. So try your best to present equations if possible. So also have, okay, usually a paper have some experiment validation. So if have, so also conclusions. Okay, in this Google Docs, okay, I provide several topics. So you can select your topics. So first the first the service. So I provide quite a few topics here. So for example, okay, okay, Chen Jun. So you can put your name. For example, if you select this paper, you want to present this paper for like 15 minutes for present and 5 minutes for QA. So put your name, student ID here. So first come first service, okay? So you can have access to this link. You can have access to this link from the lecture notes. So of course you can download the lecture notes from the Blackboard. So in the courses, this content, you can find the week 9. So for week 9, okay, you can have access to this link. So put your name for first come first service, okay? Any questions? For example, we provide 18 topics. So it should be good enough. So for example, if you want to select some topics that is not included in this table, it's okay. So as long as your topic is relevant to the navigation problem, okay? Like the drones for DJI or drones for like cars for Tesla or for Google's auto-driving cars, it's fully okay. So any questions? You good? 15 minutes plus 5 minutes for QA. So each of you need to prepare a slide. Okay, so it's clear, right? So from now on, so today is week 9, week 10, 11. So at least you get 2 weeks to prepare. Okay, you get 2 weeks to prepare. So this is for the presentations. So of course you can find as I just mentioned, you can find the details from this page. So for example, this is a cover page. This is the cover page of the presentation in the previous semesters. Okay. So for example, this is the cover page, and this is about this paper. Okay, published in the eCRA. So this is the academic conferences in the Robotics Society. Okay, so it's clear. Okay, besides the requirements for the presentation, so let's move on to today's lecture. So in the past several weeks, so we talk about the GPS. So for example, we talk about the shoot range, how to use the shoot range to calculate the position by least square. And also in the last week, we talk about how to use the differential technology. Okay, so if you get the data from reference station, so you can make try to eliminate some error turns such as the crop bars. So from last week, I still received quite a few inquiries about like did not really understand the least square process. So for example, like if you have a GPS, so based on shoot range, we do the iteration to do the tail expansion, blah 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 something. So I find like some of the students still it's not clear how this happened. So the schedule for today is going to be like this. So I will start with example. So how to formulate a least square problem or solution to solve to find the extreme point for a quadratic function. So the second part is like based on this similar process. So how to calculate the velocity, or how to calculate velocity of the GPS receiver. So in the last week, we talked quite a lot about positionings, right? Like 5 centimeters accuracy, like several meters accuracy based on the raw data. So today we are going to talk about how to directly with the so-called the Doppler measurements, okay, from GPS to calculate the velocity. So let's start with the examples first, okay? So let's start with very straightforward or simple examples like how the least square process from linear to nonlinear. Okay, so for a linear case, okay, so for example, I provide two equations. Okay, 3x plus 4y minus 2 is equals 0, and 4x minus 5y minus 10 or plus 10 equals to 0. So this is a typical examples like the linear case, because for all the coefficients and the exponential, there's no exponentials here, right? So this is the linear case. So of course we can write this into the matrix form. Okay, 3x plus 4y equals to minus 2, and 4x minus 5y equals to, okay, make some movements, you get this one, right? So you can write this into the matrix 3, 4, and 4 minus 5, and x, y equivalent to minus 2, minus 10, right? Is that correct? So for this case, okay, if you cannot see, my handwriting clear, you can just sit in the front. Okay, I will not ask questions. No worries, okay? You can sit in the front if you cannot see it clearly. So for example, this is examples. So the physical meaning for this, is going to be like, okay, x is like a two function. Okay, they have an intersection, is it? So this is, generally the physical meaning of the two equations is like this. So because everything is linear, right? So this is a 2 by 2 matrix. For example, this is A matrix. So this is a 2 by one matrix, for example, let's say x. Okay, the uppercase, the unknown variables, right? So the right side is a B. Okay, maybe this is a 2 by 1 matrix. AJ. So in this case, the X 2 by 1 matrix can be calculated by the inverse 2 by 2 matrix multiply B 2 by 1 matrix, right? So because A is a square matrix, so you can solve it. Okay, do the inverse directly because the square matrix you can do the inverse, right? So the physical meaning for this one is to find the intersection, point. Okay, for this one, right? Okay, so let's do a linear case. You don't need to do any like linearization like process. It's not necessary. Okay. If I change the formats, okay. If the problem is like if I define, okay, this is f(x,y), this is f(2,x,y). Okay, if this is two functions, right? So for this function is relevant to the x1, x and y. For this equation is related to x and y, right? So how can I find x and y? X and y star means the base, okay? To minimize, okay, I try to minimize the square roots of f1x y plus f2x y square. So this is more like the GPS problem. Okay, you get two measurements. Okay, but the solution is still is the same as the previous equation, because if you make this equal to 0, you can solve this equation to minimize, right? So in this case, the minimize this going to be approaching 0. So if this is 0, this is going to be minimized, right? But still, to solve this equation, you can do the same thing, okay? So to make this to be 0, still you can write down the equation 3, 4, and 4 minus 5, x, y. Okay, and you get 2 and minus 10. Just in one go. It means one iteration is good enough, okay? Just one iteration. This means it's like no iteration, just one time. Okay, you can get the analytical solution. So this is called analytical. Okay, this is analytical solution. Directly get this. This is A, X, B. Okay, the X is equivalent to A inverse multiply B, right? Is that correct? Okay, so this is the linear case. There's no iteration, just in one go, okay? One time you get the solutions. So for the nonlinear case, so if x is equivalent to x minus 2 square, okay? So the physical meaning for this equation is, so this is x square, right? X fx, this is y, okay? So this is x square, right? So x minus 2 means, okay, you shift away a little bit. Okay. So, I mean, generally, so the solution, if you want to make this to be minimized, it means 0, right? If you want to minimize this one, okay, the solution is, of course, s is equal to 2, right? Okay, this is one dimension cases. So if I make this to be slightly more complex, okay? If the solution is x, if the problem is x minus 2, okay, so if I want to minimize this equation, the solution clearly x star is 2, y star, the solution is 3, right? This can be minimized. So the physical meaning for this equation is going to be like this. So it should be the two-dimension case. So the physical meaning for this one is like this is X, this is Z. So it is a Y. Okay, this is F, X, Y. So the solution is 2 and 3. Okay, this is the extreme point, right? This is extreme. So it's going to be like this. Isn't it? So this point is the extreme point to make this approaching 0, right? So if I make this even more complex, okay? If I make this even more complex, you still can solve it? So how to find the extreme point to make this to be minimized? To make this to be minimized. I mean, from the first sight, you cannot find the solution, right? So this is the nonlinear case. It means you need to find a way to solve it, to minimize this. Like, okay, maybe make it to be 0. So what is the solution? So what is X? What is Y? To make this to be minimized. We have no ideas, right? Because this cannot be like just in one go to solve it. So in this case, okay, let's go back to the example, okay? If this is X minus 2 square plus Y minus 3. Okay, so can we use some like least square or the iteration process to minimize this function? So, okay, so as we know, this points 2 and 3, right? So at the beginning, for example, okay, you give this problem to the computer or to a laptop, okay? It don't know how to start. So I just set the initial guess. Okay, I just guess. Okay, initial guess x0 is 0, y0 to 0. This makes sense, right? I just guess. Okay, I have no information about what is the base solution for this. What is the base solution for this? Okay. But the great thing is I can do the iterations. So okay, so as we mentioned for the Taylor expansion process, okay. So given a function f x y, given a function f x y, okay. So for any of the function, so the Taylor expansion concept is like if the linear integration point is xy, and for any delta x plus delta y, this is equivalent to x, y plus the partial differential, okay? Is multiply x minus x, sorry, this one is like x minus x0 is delta x plus isn't it? So this is, this is the Taylor expansion process. So it's clear. Do I need to start with the one dimension cases? It's okay? It's okay? Clear? Okay. So for this case, of course, we can write this to the matrix. For two dimension cases, J, maybe this is going to be JT. Okay, so the JT here is going to be isn't it? So if you write down this, okay, you can see the screen on the back. You can see the screen on the back? Yes? Okay. So for this one, it's a 2x1 matrix, right? So this is fxy, right? So the physical meaning of the least square process is like, so I have no information. I just guess my first point, my initial guess at 0, 0. So for example, for one dimension cases, x and y. So for example, this is a typical y equals to x squared function. So for example, if I start from this point, if this is this is the extreme points, right? Because for this one, it's f x dot equal to 0. So this is the extreme point. So if my initial guess start from here, okay, start from here. So if I want to approach and find this extreme point, I should be do some like gradient descent, okay, to find this point gradually. So for example, for the first iteration, I find the delta x to find this point. So the second iteration, find the delta x to gradually find the delta x to finally, okay, approaching this point. So it means, so for this function, it means fx plus delta x, y plus delta y should be equivalent to fxy plus jt delta x delta y. Is it? Is that correct? Okay, so for the simplification, so if I define this as like delta x delta y, like define this is a delta p. Okay, so for the simplification, if I define f plus delta x, that should be equivalent to fx plus jt delta x. So in here, okay, x is equivalent to delta x delta y. So I mean, delta x can be the one dimension case, also can be 3 or 4 dimension case. Okay, just for the simplification, okay, I write down like this. So delta x can be the multiple dimensions. Okay. So if I want to minimize, if I want to find the delta x to minimize this equation, this means I want to, the problem is going to be like, okay, minimize. I try to find the base delta x to minimize fx plus delta x. I want to minimize this. Minimize this. It means, okay, plus the square, plus the square. If you want to minimize this, it means you want to minimize, okay, this is fx, okay, square. Is that correct? Square means you want to multiply one more thing, okay, fx jt delta x. So because this is a, I mean, this is a matrix. So for example, for a matrix, A square is going to be A transpose multiply A. So this is the base theories for the matrix calculation. So in this case, if you want to calculate the square, okay, there's going to be one more transpose here. So in this case, we can, okay, calculate the square is going to be like fx square plus fx multiply this one and this one, okay, plus this one multiply this one, you get fx jt delta x plus jt delta x. Okay, so for this one, you get a square here. So if you want to make this to be minimized, it means you want to make sure, I mean, for this point, the gradient is approaching 0. So this is, I mean, the basic assumptions for the extreme points, right? For the extreme points. It means you need to make this, for example, okay, this is a new function, fx. So you need to solve the function of fx approaching 0, because for this function, okay, for this function, you want to calculate the delta x. Is it correct? So in this case, you want to find the base delta x. You just want to gradually approaching the extreme point, this iteration process. So you need to make sure you find the delta x to make this gradient to be 0. Because this is the basic assumptions that you want to find the extreme point. So in this case, so for this one, if you calculate the partial differential, this is going to be, okay, let's see, delta x. So for this one, it's not related to delta x, right? So that's going to be nothing. So it's going to be fx multiply jt and plus, okay, this is the same, okay, 2 here. This one is the same, right? So in this case, there is a 2, okay, coefficients in the front. So for this one, okay, calculate the partial differential. It's going to be 2jtj multiply delta x equal to 0. It's clear from this equation. So okay, I will go through again. So in this case, finally to solve this equations, it means you need to, okay, you can eliminate the 2's, right? Fx multiply j transpose plus j t j delta x equal to 0. So in this case, it means you get the j t j delta x equivalent to minus fx j transpose, right? So in this case, the delta x should be equivalent to j inverse, okay, multiply minus fx jt. Okay, so in this case, it's equivalent to minus j inverse fx j transpose. So for the fx, this is a scalar, okay? So this is a matrix. So finally, you get the equation is minus fx multiply j. Okay, so this is finalize the solution. So based on this, so this goes through this again. For example, okay, given a function, if I provide a function like this, so how to find the minimize the value of the fxy? So I have no information. So generally, so for example, if this is the one-dimension cases, so for example, I have no information, I just guess. Okay, I just guess like if the problem is x, y. For example, this is 8. For example, if the extreme point is like this, y equivalent to x minus 8 squared. So I just guess the initial guess is at 0. Okay, so okay, of course, the fx here is like should be, for example, if x is approaching 0, this value is should be 8 squared, right? So this is not minimized. So I try to find the delta x, okay, for the first iteration to gradually like for example, okay, later I will start with the example, okay? So the first iteration delta x, second iteration delta x. So maybe like 4 iteration, you will converge to this point gradually. So based on this assumption, so I do the Taylor expansion for the equation. F plus the delta x should be equivalent to fx multiply the gradients, the partial differential multiply the delta x, right? So from this equation is clear? It's okay, right? So if you want, because I want to minimize this Taylor expansion, it means you want to minimize, okay, you can get this square root function. So this is a general form, okay? So get the square. So for example, like if you calculate this square, you're going to get this. And the estimate point, one of the properties f dot x is approaching 0. So this is the basic assumptions for the estimate points, right? So in this case, you can find, okay, you can get to this. So make the gradient to be partial differential to be 0. So finally, you write down the matrix, you get this equation. Okay. So finally, you'll find, okay, the delta x should be equal to this one. So the j is the partial differential. So the j is the partial differential. So this is the, so I mean, this page is the what you can see from books, but in the this is the content I delivered in the last year. But if I start with those parts, the student feel it's hard to understand. So that's why from this year I didn't mention this I mean the basic formulation of the equations. So for example, in the previous week, do you still remember how to introduce the least square process? I start with the Taylor expansion. Because I think that way will be much easier to understand. But I'm not sure which one do you prefer. For example, this is much easier to understand. So this is to calculate the delta x. So this is called least square solution. The most general least square solution, or you can call this is Gaussian-Newton. Gaussian-Newton. You can search from Wikibyte. So the final solution is like this method, okay? So this method can almost solve all the nonlinear problem you encounter in the future. Trust me, you can solve almost all the problem. But the problem may be like, if you have some highly non-convex problem, the solution may not be globally optimal solution. So, okay, so let's try to use the equations on the right side to solve it, okay? So it's, so can I erase this one? It's clear? Okay, let's start with the example, okay? Okay, so if the problem provides, if the problem is this, okay? So I want to find the point. I want to find the, okay, the extreme point. So of course, it's quite clear. The solution is x star equal to 2, y star equals to 3. But for the, I mean, for the computers, they don't know how to solve this. So for the computers, they don't know how to solve this equation. Okay, take break for 5 minutes, okay? Okay, take break for 10 minutes. So feel free to comment if you have any questions. Yeah. Feel free to let me know any questions. Also, okay, if you have any questions for the presentation, okay, also feel free to let me know. is understandable for this time? Still maybe? Still not clear? Okay. Yes, so the logic, so after you do the linearization, after you do the Taylor expansion, it's going to be a linear problem. So if this is a linear problem, it's going to be the first case. You can directly do the inverse between that. So after you do the linearization, for example, if for any number, okay. So for example, if AX equals to B, A is the G matrix here, okay. After you make this problem, if you do the expansion, so this problem is going to be transferred back to a linear problem. So in this case, you can directly solve it by A inverse B. Okay, this is the case as A is n by n matrix. So if n equals to n, if the case is like A m by n matrix, okay, m is not equal to n and m is larger than n. So this is the case that x is equal to A transverse A minus A. So this will be the case. If this is not a square matrix, you need to do the log. This process is called the inverse. You see, because after you do the linearization, this is going to be a linear problem. Locally, it's going to be a linear problem. Okay, no worry. Look, I'm going to start with the example with real data. It's easier to understand. You're from A or E, or U4. Yes, please. Transpose. Transpose. So, for example, okay, if the matrix, okay, if the J matrix is okay, this is n by n matrix. Okay, so if you calculate the J square, you cannot directly. You see what I mean? So because J is m by n, if you directly calculate m by n, this is not doable. For example, if you do m by n multiply J by transpose, so this is m by m. So in this case, you can do multiplication. That's the point. You have another linear algebra. How much you get? A grade? I don't think I think you know how to do the calculation, but don't really know the physical meaning of those matrix calculation. You know how to do the assignments, you know how to do the projects, but you don't really understand the physical meanings. The physical meanings in front of those matrix calculations. So I think okay. So I think you are quite smart to select select this course, because this course is like we directly use the theory you have learned from linear algebra to the real problems, like the GPS problem. Okay, no worries. I will start with the data later. No problem. So you're from ME. So do you have a chance to learn those like the nonlinear least square of any subject is going to take notes? So I never no lecture like this to introduce linear least square no. This quantity, I mean, linear is this. I think it's totally some TMA process, not in ME. You mean this glossary for M? Okay, see. And also, if you directly introduce the script, maybe without any example, this data is also with the physical model. Yes. It's going to be boring and harder than if. Okay, so let's go back. So one more thing I want to emphasize. So in this course, actually, we only learn two things in this course. The first one is a model. The second one is calculations. So the model means, for example, we learn about like the shield range. So this is one equation, right? This is a physical model. So for the later today, we are going to introduce the Doppler measurement. So the Doppler measurement model. So this is one more model. So for the Wi-Fi, this is the model, right? So you see, so finally, we are going to get quite a few equations. So those equations are obtained based on the models, right? So this is the first part we learned from guidance navigation, this course. So the second part is like how to solve it. So get a model, essentially it's going to be the problem that should be go back to the mathematics. So for example, okay, so this is an example like quite non-linear case, right? A lot of like square roots and power two coefficients, blah blah. So this is, I mean, essentially this problem is the same as the GPS. I mean, essentially because there, I mean, after you do the modeling, so finally it's going to be the same. Okay, so let's look into this problem. Okay, I mean, okay, intuitively, this solution is like x star 2, y star is 3, right? So how can we solve it, this equation based on the I mean, like the least square process? Okay, let's do it, okay? We can get a solution like within, I say it should be within 6 iterations, okay? But for a computer, okay, it's just nanoseconds. Solve it in 6 iterations, just nanoseconds. Okay, but for me, okay, you can just look into the time. Maybe I need to use 20 minutes to show you the process of the gradient descent. Okay, so let's start. Okay, this equation is the core equations. It's a core equations. Okay, so for the I mean, let's start with the first iteration. Okay. Okay, for the first iteration. So 1.1. Okay, initial guess. Okay, at the beginning, so the laptop or your computer have no information about what is the solution. So you can just intuitively set x0 is equivalent to 0. Okay, y0 is approaching is equivalent to 0. So for the if you calculate the gradients, so the j is equivalent to is it? So this is a 2 by this is a 1 by 2 matrix, right? So this is equivalent to what? Okay, so if you calculate the partial differential for this equation for x, so it's going to be 2 minus 2. Is that correct? So I mean fxy is this one. Y minus 3. So if you want to do the partial differential for this equation with respect to x, this should be, because this one is nothing related to x, right? So let's see 2 multiply x minus 2, 2x minus 4, is that correct? So in this case, this equation is 2x minus 4, right? And for the second part, okay, for the y, is equivalent to 2y minus 3. Is that correct? So because for y, this is not related to the y. So in this case, we only need to do partial differential for this term. You get a 2y minus 6. This 2y minus 6, this is a 1 by 2 matrix, right? So for the J transpose is equivalent to 2x minus 4, 2y minus 6, 1. This is 2 by 1 matrix, right? Okay, so for if I set the initial guess to be 0, 0, in this case we can calculate the f0 x y, and x equals to 0, y equals 0. This is going to be, okay, put into this equation, minus 2 square plus 0 minus 3 square, okay? That should be equal to, okay? So please correct me if I do some typos, okay? This is correct, right? So in this case, you get, it means in this equation, you get the fxy, you get the jt. So in this case, you can calculate the delta x should be equivalent to minus jtj minus fx. So as we know, so for this one, jtj means, okay, for, in this case, we can calculate, okay, so the j is, this is 0, minus 4, this is 0, minus 6, okay? So the jtj is equivalent to 4 square plus 6 square. Is that correct? So jtj means you calculate the square norm. So this 16 plus, did I do some typos? No? It's still correct, right? 36. So in this case, let's going to, okay, something like this. So this is going to be minus, okay? So this is going to be equivalent to 1/52 minus, is that correct? And fx equals 13, okay? Okay, let's minus over here. So this is going to be 4 and 6. JT. Okay, it's JT, right? So in this case, okay, that's going to be 1 and by 2. Is that correct? Okay, so in this case, it means you get the delta x is equivalent to 1.5. So the physical meaning is like, okay, you start from this point, okay? It's like you're gradually approaching this point. For the first iteration, you get to this point. So it should be x is, so in this case, the first iteration equals to x0 plus 1. So x1 equals to 0, 0 initial guess plus delta x is going to be 1.5. So it means after one iteration, you iterate from this point to this point. This is 1.5. You see, after you do one iteration, so the point is approaching the extreme point. Okay, gradually approaching. So one iteration, okay, the solution starting from 0 to this point, right? Okay, so for the next iteration is going to be, so for the next iteration is, this is going to be, okay, you can reuse the initial guess as this point. Initial guess is, okay, 1 and 1.5. Is that correct? Okay, initial guess is this one. So this is the same. Okay, this is unchanged. This is the same. So this is the same. So in this case, this is going to be 1. This is going to be 1.5. So for x, this is going to be the first iteration. x1, y1 is 1. So this initial guess is based on the previous iteration, right? So is it okay for this? Is okay, give me some feedback. It's okay for this. Okay, so in this case, you can calculate this. Okay, so this is equal to 1 square. This is 1.5 square. Should be, is that correct? Okay, so this is going to be fx. Sorry? 3, yes. 3.5. 3.25. So in this case, so for a j is going to be slightly different. So 2, okay, if x is 1, it means this is going to be minus 2. Okay, this is very interesting, okay? Okay, so the j0, let's mark down the j. So the j0 is minus 4, minus 6, right? So the j1 is going to be, if this is 1, it means minus 2. And this is 1.5, it means minus 3, right? You see the gradient is decreasing. It's like, so gradient for this point, okay, go down. The gradient is also decreasing. So you try to minimize the gradients, okay, to make the gradient to be 0. So, okay, let's go back. So if this is a gradient, it means you can calculate the JTJ. So for this one, okay, for this one is going to be 4 plus 9 is like equals to 13. So in this case, if you get to the JTJ, which means that's going to be minus 13, 1 over 13, and multiply minus 2, minus 3, fx is like equal to 3. So in this case, this is going to be, is that correct? Okay, so in this case, this is going to be 3 point. That's a problem. Okay, it's a good number. Okay, so in this case, you see, so the movements, so the first delta x and gradient is descent. Okay, decreasing. Okay, gradient is decreasing. So I mean the norm of the J0, the norm of the J1, So this is decreasing, right? The delta x is also decreasing. So delta x is like the values, the norm of the delta x is also decreasing. So, okay, so next solution is going to be x2 is equal to x1 plus delta x. Okay, the first one is 1.5 plus. Okay, so this is going to be 1.5 and which means the next point is going to be moved to the maybe this point, okay? So the value of this one is like, you see, the value is much close to the exact solutions, right? So this should be equivalent to this one finally. Much close to this one, right? So similarly, if you do the iteration like 2 more times, so the value will be equivalent to this one. The value will be equivalent to this one. Okay, so this is, so it's clear for this page, right? Okay, so let's go back to the equations for the GPS. So if you still remember, the model for the GPS is receiver to the satellite is equivalent to x minus x satellite plus y minus y satellite. Plus I plus t plus noise plus the c multiply something like this, right? So for this equation, okay, you can move this rs to the minus. You want to minimize this equation to calculate the x, y, and z. It's the same. It's just the same for this. Okay, you also want to minimize the equations. So if you get the should the range measurement from multiple satellites, okay, we do the similar iteration process. Okay, so let's make a practice. Let's make a practice, okay? So if this is changed, okay, please, okay, do the practice from yourself, okay? So to follow the similar process to calculate this minimization problem, okay? Calculate the xy to minimize this equation. So finally, the solution should be, the finalized solution should be x should be equivalent to 2 by 3, 1 by 4. Okay, so please do it. Take try. Okay, take a try, okay? Anyone have get the result? Very close right there. So how many iteration you have done? Oh, just two. It's not enough. At least four, I think. How many iterations? Oh, it should be. Big macros. Oh, you already get the solution. Should be y should be 1/4. What's up? Very close. It's very close. Okay, so answer. So let's have a quick relation for this one. So okay, the major difference is for this problem and the previous problem is the coefficients is different. So the coefficients will affect what? So I mean, so calculate the delta x, right? So the major difference is the j. So the partial differential Jacobian matrix is going to be different. So for example, for this problem, the Jacobian is going to be okay, 6x minus 4 and 8y minus 2. It means for this problem, it's going to be thinner, okay, much sharp. It's going to be like this because the gradients or the curvature is like larger comparing to the previous one. So if you replace the j, you can do the exactly same process. You can do the exactly same process to get to the finalize the solution. To get to the finalize the solution. Okay, so after we have introduced this, okay, let's go back to the problem from GPS. It should be much easier to understand. I mean, at this moment. Also, you can after lecture, you can ask this question to ask a ChatGPT to also ask ChatGPT to provide the Python code for you to solve this problem. Okay, immediately in nanoseconds, you will get a solution. Okay, so let's move forward. So this is the data. Okay, so the data we collected in the last tutorial in the lab. Okay, so this is the timestamps. So it means 2024. This is the year, months. Okay, day, and this is the hours, minutes, seconds. Okay, 5.9 seconds. Okay, we receive. Okay, you see quite a few satellites. So the G means the GPS. Okay, the index 10 means the index of the satellite. So it means you receive 1, 2, 3, 4, 5, 6, 7, 8. 8 GPS and several grounders, and the C means the Chinese Beidou. So those are the satellite missions received. So this is the shoot range. This is the distance from the satellite to you. Okay, this is the shoot range. So this is the this is so-called the Doppler measurements. This is so-called Doppler measurement. So, sorry, this is carrier phase. So this is Doppler measurements. So Doppler measurement is another terms I want to introduce. Okay, in the coming minutes about how to use the Doppler to estimate the velocity. So this, okay, look one more time for the GPS. So as we mentioned, okay, so the GPS should range can be modeled like this, right? So generally, this can be modeled it's around like 7 meters, right? So finally, the problem is going to be like receiver to satellite. Okay, so this is the measurements. Okay, this columns. Okay, minus square roots. Okay, this one, right? plus I plus t plus speed of light. Okay, you want to make to be 0. So you want to calculate the x, y, z to make this to be 0. So this is for the maybe for the first satellite. Okay, first satellite is G0 or G10. Okay. So for the next satellite, okay, the next satellite is G23. Okay, you again get the equations. You again get the equations. Okay. So as we mentioned previously, so the J matrix, okay, the J matrix can be calculated, okay, can be calculated like this. The J is exactly the same as the J in this equation. So the J is the partial differential, x minus satellite minus this one, and this is the square norm, okay? And x, y minus y, this is the same square norm. Z minus this is square norm, and this one should be the speed of the light, okay, corresponding to receiver clock bars. Okay, so this is for the satellite G10, G23. It's going to be okay for this row. Okay, for this row, S is equivalent to 10, S equivalent to 23. So this is the index. Okay, it's not the coefficients of the power. So this is X. For example, this is 23 minus X minus Y. D23 minus. Okay, speed of light. So for other satellites, it's exactly the same. The major difference is change the position of the satellites. And the square norm is also you need to change the position of the satellites. Is that correct? So if you get this, you can iteratively calculate the position of a receiver. So for example, at the beginning, you can set the initial guess of the X, Y, Z, and receiver clock bars to be 0, 0, 0, 0. If you go back to the slide for the single positioning, you can finally, okay, do the same thing to get the solutions for XYZ. For XYZ and the receiver clock bars. So if we finish the positioning problem, okay, finally, if you finish the positioning problem, so this J matrix is a non-variables, right? Is that correct? If you solve the positioning, so if you solve the single point positioning, okay? Okay, single point positioning means point positioning means you directly solve the position XYZ based on the shoot range. So at this stage, J is a non-variables. Okay, so let's introduce another model for the velocity. Okay, so if you look into this page, this row is the Doppler measurements. It's a Doppler measurements. So as we learned from high school, the model. Okay, just now I mentioned two things. In this course, you learn two things. The first is the models. For example, model for GPS shoot range, the model for the Wi-Fi IDT. Okay, this is the model. So for the mathematics, it's like okay, iterative least square. So in the high school, for example, okay, so this is like okay, if this is the signal transmitter, okay, the signal is like transmitted to and there's a car, okay, moving is a given direction. For example, this is like okay, s represented by s with a velocity. Okay, if this is 0, okay, static. If this is a car, velocity is vr. Okay. If the signal, okay, if the frequency of a signal is represented by s, fs, so the frequency, okay, so the unit is by hertz. So if this is static, okay, the signal frequency received by the cars, f r, okay, should be the same. The frequency should be the same. If the velocity of this car is not zero, okay, there should be an equation. The equation should be kind of v r minus vs. The physical meaning should be kind of like this. Which means the bigger the bigger speed differences is going to be, introduce the more significant change in terms of frequency of a signal. So this is what you learn from high school, right? So this is a signal transmission from this transmitter. So if this is static, it means if this is zero, this is zero. So the differences, the differences Fs minus Fr, okay, with a wavelength. So wavelength is a coefficient of a signal. So those differences should be approaching zero. If the velocity difference is zero. So this is from high school, right? If the relative velocity difference is big, the change of the frequency of the measurement will change. So this is similar. Okay, let's go back to the GPS problem. Okay, so this is the Earth. Okay, so there is a car. Okay, with like velocity is like this. Okay, this may not be reasonable. Okay, with velocity that is parallel with a tangent space direction, and this is a satellite. Okay, so for example, satellite is moving with a given velocity. This is vs vector. Okay, so the vx vector is represented by x. This direction is represented by v x s, v y s, v z s. Okay, by a three-dimensional vector. Let's to represent the velocity. Okay, represent the velocity in each direction. So for cars, we are this represented by. Okay, so let's say the velocity of a receiver or the car, and this is the velocity of the satellite, right? So this is a direction vector. Do you still remember the direction vector of this one? Okay, of this one can be represented by what? Okay, so for example, this vector is called receiver to a satellite. Okay, so this direction vector from receiver to a satellite can be represented by, direction vector means the norm is equivalent to 1, okay? This is equivalent to the square norm distance. Sorry, x satellite. And this is y satellite minus yr. This is the satellite position x. Let's set the receiver position y. And the ds minus cr. So the square norm is x minus y square plus something, okay? So this means the distance from satellite to receiver. So this direction vector can be calculated based on this, right? Okay, so for example, if you represent the square norm of this as p, okay? So the p should be equivalent to the square root of xs minus x plus ys minus y square plus ds minus z. Isn't it? So this is the square norm distance from the satellite to receivers, right? Okay, so it's clear at this stage. Okay, so as I mentioned, if you solve the positioning problem, the receiver's position is already a known variable, right? So in this case, this direction vector is non-variable because the position of receiver is non-variable. Okay, so based on the physical models of the, okay, so this is Earth. So the physical model, I mean the change receiver to a satellite, the change, because I mean the radial signal from satellite, okay, this is a radial signal. So that is giving frequency. So the change of the frequency is, okay, from satellite to the receiver. Okay, this is the data frequency of the GPS signal from signal transmission and received by the receivers. So the change is going to be directly related to the multiply the velocity of the satellite minus the from receiver. Okay, satellite receiver should be like this. Okay, plus this one should be called the, because your receiver have a drift, have a clock drift, so you should have a clock drift receiver. Okay, clock drift. This is so-called clock drift. So this is the physical models for the Doppler measurements. Okay, this is because of speed differences. So for example, if the speed difference is between the two systems is 0, okay, this is also going to be, this part is going to be 0. So because the motion differences, for example, the direction is different and the magnitude of the velocity is different, so we have the Doppler measurements. So the Doppler measurements, this one is corresponding to this row. You see, this one is quite small, right? So this is the cases that the differences of the motion is quite small. So in this case, we get this measurement model. So this is so-called the Doppler measurement model. Okay, so let's look into this equation to see which one is the unknowns. So left side, okay, this is the measurement. Okay, this is the non-variables. Left side is the Doppler measurements, right? So this is also non-variables because you mentioned if you solve the GPS positioning problem, the direction vector connecting the satellite to receiver is a non-variables. So this is non-variables. So satellite velocity, okay, it's a non-variables because we know the position of the satellites very correct, very accurately. So the unknowns is the velocity of a receiver. This is unknowns. Another unknowns is this one, okay? The clock drift. That means the differential of the reciprocal bias. So in this equations, you see, you have like 3 unknowns in this equation because the VR means the position, the velocity of the receiver, XYZ. So, and also one more unknowns. It means for one Doppler measurement, you get 1 equations and you get 4 unknowns. You get 4 unknowns. So this is kind of very similar to the short range problem. Okay, so let's look into. Okay, so let's look into the physical meaning of this equation. So as I mentioned in for the Doppler effect. So for the Doppler effect, I just mentioned in the 1-dimension cases. Okay, so for example, this is an example. Okay. So this one is better. So for example, this is a satellite, okay? The same satellite. So, okay, for example, this is Chen Jun, okay? You just static here, okay? I receive a signal from satellite. The data frequency is around like 15K. So if I was, okay, running with a given speed, so data frequency I receive is going to be different. Why? This is due to the motion differences because you have velocities. So if I static here again, which the same as you, so the frequency of the data I receive is going to be the same. You see the differences is coming from your velocity. That's good. It means the measurement you receive is associated with your velocity. Let's provide the clues for you to calculate your velocity. So this is, this is the model. Okay. So after you get this model, okay, let's take a look on the physical meanings. So delta FRS is okay. So if you look into this equation, so S is so if this is the vector of the satellites, if this is the speed of the okay, for the first part, okay, the minus of the two vectors. So you all know, okay, if this is a vector, this is a b vector. A minus b means what? Means this vector, right? Is that correct? Okay, from linear algebra. So this is the calculation. So for this one, okay, v satellite vector minus the VR vector. It means, okay, you can, okay, because this is a free vector, you can move, okay. Because this is a free vector, you can move this to the same starting point. Make sure they are parallel. Okay, so the minus is going to be, sorry, this, okay, move this vector parallel with this one to this point. So the minus is this one. It's the same. Okay, for example, move this, okay, to this one. You get this vector. This vector is VS vector. Okay, the minus. Okay, so the minus means the physical meaning of this part is going to be this new vector. Is that correct? So this vector multiply with a vector means what? Multiply means what? For example, okay, if this is a vector A, this is a vector B. So the multiplication of A multiply B means A, the norm of A and the norm of B cosine theta means project this to this direction, the projection. This is the projection, right? So in this case, this, okay, this part is this one. So multiply the direction vector means you try to project this vector to the direction vector between the satellite and the receiver. It means you project the velocity differences to the direction of the long side connecting the satellite to receivers. Okay, just one more time. So this is the velocity of the satellite, right? This is the velocity of the receivers. So the minus is going to be this new vector, right? You multiply the speed, you multiply this vector is also kind line of sight, because this is directly connecting the receiver and satellite. So you try to project this vector to this direction of project to this long side vector. So to see this means how much, because the signal is transmitted in this direction, it means how much your velocity differences is by projecting back to the line of sight vector. So this is the physical meaning. So for example, do you remember I mentioned the one-dimension cases? Okay, so for example, this is a one-dimension cases, right? Because the radial signal will only transmit through a single direction. Okay, so this equation tries to reformulate the three-dimension case to one-dimension cases. So the one dimension is the direction connecting the satellite to a receiver. So this is the physical meaning. So okay, I mean the mathematical equations is always beautiful, but I mean if you want to understand the physical meaning is like this. So try to project the velocity differences to the direction vector. Through a direction vector. Okay. Okay, so this is the physical meanings. So as we mentioned, so for this equation, okay, for this equation, you can, so because for this one, I mean, the unknown is the only unknown is the receiver's velocity, right? So you can define, okay, a new function, Vx receiver, Vy receiver, Vz receiver, and also the delta R dot. Okay, the new equation is, okay, move this to the right side, minus ERS direction vector, multiply V satellite velocity minus V receiver. You see, this is the function, exactly the same as this one, right? The unknown here is xy. The unknown here is the velocity of the users, right? So okay, one satellite will contribute to one equations. You see, one satellite. Okay, in this case, in such kind of scenarios, okay, you receive like, okay, from 28 to 48, at least you receive more than 20 satellites. It means you get more than 20 equations like this. Of course, you can calculate the Jacobian J, right? And you can solve the velocity here. You can solve the velocity here, okay? Okay, so for example, like if we put some numbers. So for example, put the numbers, the first one is like 824. This means the first function is this is going to be 824.5 something minus, and this is a non-variables, right? Because we have calculated the position VRS vector minus VR vector. So in this equations, okay, this is non-variables. This is unknown. This is unknown. Okay, this is 3 dimension, 1 dimensions for one equation. Okay, if you get multiple equations, you can calculate the J. You can calculate the J. Okay, you can calculate J. So in this case, you can calculate the velocity of the receivers. Okay, based on this Doppler measurement. So usually in the open sky, I mean the Doppler measurement can provide the accuracy of the velocity centimeters per seconds level. It's very accurate. I mean in open sky at the centimeter level. At centimeter level by solving, I mean, for example, like at least you need 4 satellites, right? Because you have 4 equations to solve it. There are 4 equations to solve it. So this is the velocity calculation, okay, based on the Doppler measurement. So also in the slide, I also present some other solutions to calculate velocity. So for example, if you have the position, so you can calculate the differences, the change of the velocity, the change of the position in 2 time steps, and okay, over the time differences, it means like you have the delta x multiply delta t, of course you can get the v, right? So this is the most straightforward solution, but this is not as accurate as this solution based on Doppler measurement. So the conclusion is, so the Doppler measurement can obtain very accurate velocity. Okay. Okay, one more information I want to supplement. Okay, so for this one, okay, to solve this problem, the Jacobian is, I mean, the J matrix is also very straightforward. So for example, if you calculate the Jacobian for this Okay, for example, for this equations, right, you want to calculate the Jacobians. Okay, so this is the, I mean, this is the three elements of this vectors. This is equals to what? This is equals to minus, is that correct? I mean, for this one, okay, this is not related to velocity. So in this case, this is a constant, this is scalars, right? So, and also last one, okay? Partial differential for second unknowns equals to, this is minus here, right? Minus, okay. Because the coefficient for this one is like this. So if you get the J, you can do a similar things to iteratively solve this velocity in 4 or 5 iterations. 4 or 5 iterations. So this is for the velocity problem, okay? So see, actually, I mean, in a slide, I put everything in detail. If you look into the slide, I redesigned the slide. Okay, I put, okay, if you learn from book, so those are from books, they say, oh, the Doppler measurement is kind of like this. It looks quite complex, right? But actually, if you really understand, it's quite straightforward. Okay, so this is the model for the Doppler measurements. So after you get this model with the data in this page, okay, you get the J. Finally, you can iteratively solve the velocity. That is, I mean, yeah, that is, it means you can calculate velocity based on all those equations. That is good enough. So in here, I also want to supplement one more examples. So this is, I mean, this is a very famous solver. I mean, it's this, I mean, this is an open source solver by the Google. Okay, it's called Ceres solver. So do you know Ceres? This is the name of the star. Okay. Okay. So the Ceres solver is so personally, this is my favorite solver. I use this solver since my PhD to solve lots of nonlinear problem from GPS to visual positioning to LiDAR positioning stuffs. So this is a good example. Okay, let's take a look on this example. So for example, I have 4 equations. I have 4 equations here. So it's like the Doppler problem. For example, the first equation is from first Doppler measurement. The second equation may be kind of from another satellite, but the model is slightly different. So the third equation means the third satellite Doppler measurement. So it's first 1, 2, 3, 4, 5 satellite measurements. Okay, so we can still calculate the J to iteratively solve it. So let's take a look. Actually, I mean, you enjoy almost you enjoy the benefit from this equation every day. So for example, if you open the Google Map, or Google Map for scheduling, they solve a lot of like optimization problem. For example, how to scale, how to do the path planning. Okay, for the path planning problem for different solutions. For example, one of the problem is called the optimization based path planning. So finally, it's always to be a nonlinear optimization problem. For example, we have a lot of constraints. So finally, it will be solved by this least square problem. Okay, least square solution. So for example, if I like provide a problem, it's like a path planning problem. Path planning, okay? Path planning. I'm talking about just one more example about path planning. So for example, this is the obstacles, okay? A lot of obstacles, right? So this this is the this is the starting point. This is the end point, okay? This is the end point. So the path planning problem is that, so for example, the path planning problem is I want to find a collision free, okay? The first constraint is collision free. I should not have any collisions with the obstacles, right? Collision free. So the second one is the shortest distance. Is that correct? So the result, the output of the path planning problem is, so for example, n waypoints. For example, the first waypoint, second. Okay, this is x1, y1, x2, y2, x3, y3. Okay. Okay, so to satisfy the path planning problem, okay. So okay, for the first waypoint, so you need to make sure, okay, if the, for example, if the cars or the pedestrians go through this point, it will not collide with the obstacles. So for example, the distance from this to the surrounding, the distance from this to the surrounding obstacle should be satisfied with some constraints. For example, the obstacles, this is obstacles first, okay? So the first constraint is f1 function, okay? Should be the distance from 0, 1 minus x1. Okay, so this is the first waypoint. The distance. Okay, so this one should be maybe kind of maximized. You want to maximize this one, okay? If you add a minus in the front, that's going to be minimized. Okay, this is one of the constraint. So another constraint is the, like for example, the, okay, so this is also applicable to other waypoints. So for other waypoints, you also need to make sure we are not going to collide with other obstacles, right? So for this one, shortest distance, it means, okay, for example, the constraint from xn, yn, this constraint is the summation of the distance. The summation of the distance from this point to this point, this point to this point. Okay. The summation of the distance should also be minimized. It means the distance from x1. Okay, you can write down as x1 minus x01. Okay, so this is a distance, short distance from, okay, sorry, x1 to x2 to x2. Okay, two-dimensional cases plus all the distance. So the summation of the distance should also be minimized, right? So as long as you can formulate the cost function, you can still solve this path planning problem by using this equations. It's exactly the same. So this is the path planning problem. So the constraint is coming from the shortest distance, no collision. All those constraints can be formulated into one equations. And you summarize all the equations and try to minimize those equations. And finally, you will get the solutions. Finally, you are going to get the solutions. So see, I mean, this square process can use to solve the path planning problem as well. Okay, so this is the example. Okay, take break for 10 minutes.
it's registered. No, no, not right now. You have to almost like it's like we should put the reply from what you need to check your. Oh. Oh, right. All of them are going to pass. Yeah. I want to know. Yes. No, no, no. This is not received. This is Alice pension process. This is the general rules. This is general rules. The procedure should be. Yes, you can understand like FX is a receipt. Yes. Yeah, right. Yes, because you want to minimize something, you try to make this to be a content. In this case, you are going to have a streaming point. This is general idea. I mean, to make the project function. So the function is going to be streaming. So you can minimize it. Yes, we do partial differential for this square summation of the residuals. So I mean, uppercase f is the square of the residuals. Finally, it's the same. Finally, it's the same. You see, finally, it's the same. Finally, it's the same. They are similar, they're equivalent. Finally, it's the same. It's a okay. So for example, if you have the square roots, right? If you after you calculate the partial differential, they are going to be a linear problem. I'll forget the issue just with this page. Okay, to understand. Understand. See, this is a way to understand because I just not have clarified to you, but since you understand. So this is general forms for formulating this square. This is idea side. So after implementation, the nonlinear problem is transferred to a linear problem. You agree? So after you transfer the linear problem to a linear problem, this can be directly solved. So get to this page. For this one, it's directly solved with the quadratic functions. Because you put the square for the residuals. You start with the quadratic function and you do the partial differential problem. For me, I think this one is easier to understand. Because you transfer a linear problem to a linear case. If you transfer to linear case, it's going to be like this. You get the richest solid in one code. It's locally it's a linear problem. So let's give one code and the next iteration. Okay, so next iteration is from different initial gains, you do different linearization, you get different linearization problem, get different linear problem. Okay, you solve one code, go back to the next iteration. And the criteria to stop the equation is delta x, the norm of the delta x is approaching zero. Which means you already get to the starting point of the stream point. No. Linear is because you do the linearization. Because so what is linearization? For any quadratic function. So if you do the translation, this is the linearization process for this point. So linearize this point is a line. So it becomes a linear problem. So the f(x) plus delta x, due to linearization, is going to be x plus f. It's something like this. So the linearization function will be nonlinear. Our right side is going to be linear because this is a scalar by scalar. It's a coefficient. It's a constant variable. So this one is linear. For this one, okay. So this is the gradients. Okay. F down x. Just mean today you have done lots. I mean, this process is quite general to a lot of problems. For any nonlinear problems, as long as you can calculate the J, we solve it. So this is exactly how the computer or the MATLAB do the nonlinear optimization of it. So the computer is quite good at calculating the Jacobians, calculating the matrix. So quite efficient. So you can do this equation like in nanoseconds. But for okay, you just say you spend like 20 minutes to finish the equations. That's a good process. So for example, this is a solver. If you're interested, you can look into this solver. Like provide other examples, like the modeling for the picture, for example, camera. So the camera, so camera face. So for example, if you okay, if this is the camera, okay, for example, you have a camera, right? So this is 3D. Okay, so based on the camera, info model to a pixel, it's 3D into the 2D. So this process is called projection. This projection is highly nonlinear. So this type of carriage for the optimization is always quite efficient to solve issue. So for same, like also nonlinear model, and it can also be used to solve. So in the future, if you play with robotics, play with robotics, so first you will have access to the store. So yeah, this will be right. So this year I'm going to take the dynamic system control. I'll take it. So we deliver a lecture. Okay, so in the lecture is good. I think we shows. So the slide is good. The slide is okay. It directly okay with slide or handwritings. Not much handwriting. User handwriting is much better. User handwriting you can follow the logic of the lecturer to see the example data. The other sheet back of the new teachers. Once you have the lab or lab one. I mean for yeah, no lab. Anyway, you have so there's a midterm for the system option. Yeah, we already have that. It's not a midterm. We already did. Oh, it is. Okay. Okay. Yeah, this is one of the most difficult course in the 4 years. The sixth course should be proportion is difficult. Okay, so let's start into this one. What's that? 大家学习的话，是不是？
Okay, so let's finish the last example, okay? So then we can dismiss. So last example is, so this is a problem is four equations, okay? F1, F1, 2, 2, 3, 4. So this is very similar to the, like you receive for different satellite measurements and you want to solve the position problem. So for first one is F1 is x equals to x1 minus plus x2 f3 is okay. So generally to solve this equation, we are going to be, the problem is like to minimize, to find the base x1 star, x2 star, okay? Star means the optimal values, and x3 star and x4 star, okay? To minimize this, okay? And the minimization part is the square of f1 plus the square of 2 plus square of 3. So generally, okay, so what we need to do is to calculate the Jacobians. So how many rows is the rows is determined by how many equations you have. So let's say it's 4 because you have from x1 to x4. So how many columns is determined by how many variables you need to calculate. So let's say also 4. So the first rows is f1 S3 and is that correct? Okay, let's see it's corresponding to the F2. Also, we're going to write down for a third equation and the fourth equation. So in this case, the whole process is still the same. The first, okay, step one is, okay, you set the initial guess S1 is equivalent to X2, equivalent to X3, equivalent to X4 is 0 initial guess. So this is the first step, okay? The first step is like this. So of course, we can calculate this Jacobian matrix by, let's say it should be equivalent to equals to 1, right? So for example, the equation can be directly write down. The first part is equivalent to 1. So the 2 is n and 0, 0. So for the second equation, it's like 0, 0, square root 5 minus square root 5, okay? And this one should be 0. And this is okay, so sorry. 2 minus 2x3. Okay, and this one is slightly different, and the last one should be 0. And for third equation, for the fourth equation, it should be 2 times square root 10. And minus 2 square root 10. So in a final exam, okay, so we are going to have some simple calculations like this, okay? So for such kind of level of the partial differential is okay, right? It's okay. So to calculate partial differential for the equations like this, okay, it's not complex, right? So in this case, if you calculate the, I mean, this 4 by 4, if you get this 4 by 4 Jacobian matrix J, so you can solve this equation based on this. Okay, so after lecture, you can take try. Okay, after lecture, you can take try yourself. So for example, this is, I mean, this is done by the laptop. Okay, so this is the report. Let me explain a little bit. So if you look into these values, so the first columns represents the number of iterations, the number of iterations. So it's too small. Right? So the first row represents the number of iterations. So because I mean the equation is like kind of square, okay, quadratic function is not complex. So like 14 iterations is good enough. So you see the cost is like the cost means okay. So this summation, okay. So this is the cost. Okay, so you try to minimize the cost. You see, based on the, so at the beginning, this is the initial guess. So the cost is decreasing. Like you see, like at the beginning, it's around 100, right? So after the third or fourth iterations, so the cost decreased to like below like 0.001 something. Okay, so in the coming iterations, it's like already quite small. So as long as the cost is like around like per minus 4 is good enough. Minus 4 is good enough. So at this stage, it iterate or I mean converge already. So this okay does not make any sense. But I mean in this, it tries to show you the results. I mean if you do one more iterations, I mean the cost is almost unchanged. The cost is almost unchanged. So this one is the change of the cost. For example, from first iteration to this iteration, how the cost is changed. For example, in the later iterations, it's almost no change. So this is the gradients. The gradients means the known values of the Jacobian vectors. So this is the, you see the time is quite short, right? This should be by seconds. Okay, by seconds. It's quite short time, so it can solve this problem immediately. So I mean, because this problem is a simple problem, so you can think about like for the big problems. So no, for the artificial intelligence. So in the next year, I will teach the artificial intelligence for the unmanned autonomous system. Okay, feel free to select. It's elective as well. Okay, elective as well, and also we provide examples. So for the artificial intelligence problem, so you have a lot of neurons. Okay, so that's why you need to use the GPU. So let's go back to the mathematic problems for the training of the neural networks. So you have a lot of neurons, means it's like for each neuron, okay, for each connection between the neurons, it will provide one equations. Okay, so for example, like okay, for example, like let's look into a classification problem, okay? So if I provide a photo to you, okay, so the conventional method is that I try to extract some features from the photo, okay, for example, some age, some circles here. So the network is like lots of neurons, okay, a lot of neurons with different layers. Okay, the output is yes or no, okay, for example, a classification problem, okay? So for each of those connection of those, for example, if you look into the fully connected networks, for each of those connection, so it will contribute to one equations. You see, if you have multiple layers, it means you have a lot of equations. So it's going to be like, it's not going to be the case for this one. You see, okay, for this one, iteration time is quite small. So if you have a lot of equations, so the problem will be, the complexity of the problem will be increased with exponentially level. So it's a big problem. So in that kind of case, so this is not good enough. Okay. So to know the details, okay, you can select my lectures in year 4. So yep, this is roughly for today. So today we have like, okay, we have reviewed the least square problem and introduced the model for the Doppler measurements. So, okay, so that's roughly all for today's lecture. I will stay here for 5 minutes, and if you have no more questions, feel free to dismiss. Okay, see you next week. So please, okay, pay attention to the presentation, okay? Prepare, try to prepare. 1 week may not be enough to prepare, okay? Try to prepare in advance, okay?